Welcome to lesson 29. So we're going to talk about one sample t procedures. Translation, we're going to talk about doing hypothesis tests and confidence intervals for a single mean in the scenario where we don't know the population standard deviation. So when we want to use a t confidence interval for mu of x, we're going to make sure that we meet these three conditions. So they're very similar to the last 2 weeks. So you want a random representative sample. You want to know that your sample size is going to be big enough that the central limit theorem will kick in. And then here, you don't know sigma of x, but you can use the standard deviation from the sample to approximate it. So when you have all of those conditions met, if you want to construct a confidence interval, you would just use x bar plus or minus t star. So this is different now. It's no longer z star. And we'll talk about how to find t star. Times your standard error of x bar. So your standard error being the sample standard deviation divided by the square root of n. So it looks very similar to before. So you're going to have your point estimate, which is x bar, plus or minus your margin of error. So this entire thing here, that's my margin of error. So the example we're going to use is that sports car example. So we have 10 drivers and this is their annual mileage for the year with a specific car. And reading the prompt, so they want to estimate the average annual mileage of all drivers for their top of the line sports car. So here, estimate tells me right away confidence interval. And if I want to word this in such a way, I could say, okay, what is that average? So what is the average annual mileage for everyone driving this car? It's probably in a particular year as well. So what is, because it's a confidence interval, I want something that's open-ended. You wouldn't answer this question with a yes or no. Average, so there's my parameter. My average what? Annual mileage, that's my variable. And then here's my population, so for all drivers of this sports car. So you want to make sure that you have all of those details. So you don't want to just say, hey, what's the average mileage? Because we'll say the average mileage of what? You want to make sure it's complete. So then our steps, they're going to be the same as they were before when we were calculating confidence interval. Then we're going to say, okay, what's our parameter? We're going to take inventory. All of those steps will be the same, except instead of using a z star, we'll be using a t star. So my parameter of interest, x is the variable we're collecting. That's just annual mileage. Well, specifically in 1 year, right? In one particular year for these drivers of this car. So notation-wise, mu x. Right? Parameter should always make us think, okay, well, this is probably a Greek letter. It's going to be mu of x. And that is the mean annual mileage for all drivers of this sports car. So mean or average. My variable is annual mileage. That's what I'm collecting on each person in my sample. And then my population, all drivers of this sports car. So inventory. So here, I'm going to start with really, really basic. My sample size, 10. That's the easiest one for me to calculate. Then you're going to have to plug in these 10 into your calculator, get it to give you one var stats. The x bar, so the mean from these 10 ends up being 9,467.7 miles. So they must be doing this in the US, right? So everybody else does kilometers, it seems like. And then my standard deviation, I am not calculating this in my head. I threw this into a calculator. I encourage you to. It's going to be 2,788.301 miles. And then if I wanted to calculate, you can calculate the standard error of x bar as well. That's going to be just that sx over square root of n. So I recommend plugging this all kind of into your calculator, not rounding until the end there, because I end up getting something like 881.7382 miles, and that's without rounding. So that would be my inventory here. And it is important to know, okay, it's 95% confidence. So I'm at 95% confidence. My degrees of freedom. So this is saying, okay, well, let's factor in how big our sample is. So we have a sample of 10. So 10 minus 1, that's just going to be 9. So we have degrees of freedom 9. Critical value. So we're going to practice finding our critical value here. And towards the end of the slides, not in this particular lesson, but at the end of this week's lesson, there is a slide with a link to YouTube, like finding critical values. So here, I want 95% confidence, and I have degrees of freedom equal to 9. So what I'm going to do is, I like this particular table. You don't have to use this table, but I look at the bottom. Okay, 95% confidence is what I want. Degrees of freedom 9, that tells me what row to use. So I want to use this row. So looking, they line up here. So this is my critical value is t star equal to 2.262. So I'm not going to use 1.96 because I don't know the population standard deviation. I'm going to use t star. Now, I don't think this link works, though there's a link way at the back that should work. So here, I'm going to check my conditions. Random sample, I would say yes, we took a random sample of all drivers, although I'm not sure where their list of all drivers was, because it's not necessarily all buyers. And then, is the sample size large enough? So this is a little iffy. Like, we did have one person that only drove like 3,000 some odd miles, so they're a little bit lower, but looking here, like, this doesn't look too bad. I mean, that's an oddball, but it doesn't look too bad everywhere else. And I'm going to focus on this in a moment. And then, we don't know sigma, but we have sample data, so we can calculate SX. So this was 2,788.301 miles. So we were able to. And I mean, even if I hadn't given the explicit, like, here is the sample data, if I told you there was sample data, you should immediately go, oh, I can use T. So focusing on number 2, I want to introduce, we have a plot called the QQ normal plot. And I want you to know that just kind of looking at that histogram, it was difficult, especially with only 10 observations, to see if it was roughly normal, right? So looking here, a normal QQ plot, you're not going to be responsible for creating one yourself. Just know that we have this tool. So the closer all the points fit to the line, the more approximately normal the distribution from that sample is. And if that sample represents the population, the more normal we can assume the population is. So we have one oddball point. This is that person who only drove 3,000 some odd miles. So other than that one person, it looks pretty close to normal. So in this case, I'd say this is probably normal enough that we can reasonably use T methods here. So here we are. Now we want to calculate the confidence interval, not the confidence level. We already know that. So X bar, so what I saw, the sample mean that I saw in the sample, so 9,467.7 plus or minus, and then I have my T star, so 2.262 times 2788.301 divided by the square root of 10. If you had calculated, this is just that standard error of x bar. You can just plug that in there. So I get something like, let me see. Okay, so just showing a step in between. Most of the time when we say show setup, this is what we mean. We want to know what numbers were plugged in where. So 9467.7 plus or minus 1994.492. So I end up getting an interval. It's a 95% confidence interval of, and I'm plugging this into a calculator. Absolutely no one is pretty much expected to do this, by hand. 208, my units are miles. So the rules stay the same. I still have to put miles. And then the bigger number, so 11,462.192 miles. So there's my confidence interval, 7,473.208 to 11,462.192 miles. And within reason, you could do some rounding here. Just keep in mind, like if it's dollars, you probably want to round out to 2 places, stuff like that. And what we saw in the sample, that 9,467.7 should be smack in the middle, like exactly. So we're almost done. Now we have to go ahead and put this all together in our 2-part write-up. So here's my interval. I find it useful to have. So that 2-part is, so we have to fill in, so the 95% confidence interval for the, and here we are looking at a mean. So the mean what? Annual mileage. And then of what population? So of all drivers of this car. So I believe it's some top-of-the-line sports car. Is on average estimated to be between 7,473.208 miles and 11,462.192 miles with a point estimate. So this is just X bar from our sample of, so X bar was 9,467.7 miles. So that's our 2-part conclusion there. It's got to pretty much hit all of those points. So you need to tell me the confidence level. You can write mean or average. We need to know what the variable of interest is, so annual mileage here. And then there has to be a population in here. So the population we sampled from all drivers of this car. And then we need the interval with units and our point estimate with units. So looking here, 95% confidence interval for annual mileage of this car is between roughly 7,400 and 11,400 miles per year. So I don't know. They're not driving this car a lot of miles per year. At least it doesn't appear to be. It doesn't sound like it's like a commuter car. So this is a duplicate slide. You can ignore it. It's at the end, at the you try slides, where the links will actually work. This link won't work here. So sorry, I didn't delete the slide, just because it would have goofed up the numbering on the slides. Okay, So now looking at our hypothesis tests. So when we want to do this, it's going to be when we have a single population and we want to test the average value or the mean value for that population. So the conditions, they're going to be the same as they were for the confidence interval. So when we don't know sigma, we have to be able to have sample information so we can have a sample standard deviation. So random representative sample, N has to be big enough, and we'll talk a little bit about how big of a sample size makes us happy most of the time. In general, rule of thumb, except for next week, 30 is almost always going to be good enough for if we're trying to test or do confidence intervals for a mean. And then that's the key difference here, is we don't know sigma. So they're going to be set up much the same. This is going to look very, very similar. You can have the same hypotheses as that we saw last week. The main thing that will change is this is now a t statistic, so we'll have to use a t-table. And this is now S instead of sigma. And so when we get out our t statistic, we're going to end up using that row in that t-table that has that degrees of freedom, whatever your sample size is, -1. And we'll go through that for the car example. So car example again, but it's a little bit different. So we have this car manufacturer. They make this top-of-the-line sports car, and they want to know if that average annual mileage is different than. So different than kind of tells me, okay, it could be higher, it could be lower. And we're going to assume the population to be normal. Okay, we're good for that one condition. So here, my question of interest. So to test whether, this makes me think, if you see words like whether or if, this usually kind of goes with a yes or no type of question. And the fact that it's a hypothesis test, that tells me I need to word this question as a yes or no question. So specifically, I'm going to ask, is the average annual mileage for all drivers of this sports car different than 12,000 miles? So here, our claimed value is 12,000 miles, right? It just came from here. It didn't come from the sample. It's just some value they're interested in. It could be that if it was different than 12,000 miles, they might want to update their warranty policy, or they might want to change something. I'm not entirely sure why they picked 12,000, but it doesn't come from the sample. Mu naught, so this is a 0. That should always come from outside of the sample. So once again, so it's a yes or no question that makes that yes or no. Average or mean, and then annual mileage for all drivers of this sports car. And then this last bit, different than 12,000 miles. And that came from the different than. And so there's not one unique way to write these. However, we will be looking for all of those pieces. So again, what is the parameter of interest? This has not changed since we did the confidence interval. We're still looking at the average annual mileage. So mu is the mean or average annual mileage for all drivers of this sports car. So the inventory will change up a little bit here. By and large, X bar and S and N, they're all going to be the same. So 9,467.7 miles. S is still 2,788.301 miles. N is 10, which means our degrees of freedom, that's going to be 9. And I did not leave a lot of space here. The other thing we want to write, mu naught, so the claimed value is going to be that 12,000 miles. So that would be my inventory. And you can put the standard error where you take the sample standard deviation, divide by the square root of n. It will be the same in this scenario. So checking through here, it is a random sample. Maybe I missed this on the earlier one. We're assuming the population is normal. So because the population is normal, a sample of size 10 is going to be good enough. So yes, n is 10, but the population is normal. So I didn't leave lots of space to write there. And so we don't know sigma. So I ask, hey, do we know sigma? If you do, go straight to Z methods. Those are preferred. If we don't, if we have the sample standard deviation, then we can use T methods. So we're going to go ahead, and that's that 2,788.301 miles. So we're going to use T methods. I mean, the giveaway this week, we're pretty much sticking to T methods. So here we are. So calculate the test statistics. So it's going to be the same setup on top. So what we saw in the sample minus what's claimed. So right away, I can say, okay, well, what's claimed is 12,000 miles. What we observed, 9,000, like 467 miles or so, that is less than the claimed amount. So I know that my T statistic is going to be negative. So that's just a quick check before I actually really write anything out. So minus the claim, so that's 12,000 over 2,788.301 divided by the square root of 10. And here I get something like, so I didn't round until the end. I'm going to round here though. About negative 2.87. So what this is saying is this sample mean that we observed of 9,467.7 miles is, about 2.87 standard errors less than 12,000. So if I were to draw out, so this is actually specifically a T9 distribution because of my degrees of freedom. So 12,000, I'm assuming the null is true. So we're centered at 12,000, and what we saw was 9,467.7. I will want the lower tail. But remember, we're going to have to multiply by 2 because this is a two-sided test. So what I was getting at, two-sided test, why? Because our alternative is different than. So mu is different from 12,000 miles. So I'm not sure if we wrote that. My null is going to be really boring, right? I'm claiming that the mu is that claimed 12,000 miles. My alternative, I'm going to have mu and I'm going to have 12,000 miles again. But we said different than, so that's why we have a not equal sign. So this is two-sided. So you might notice we have our T-stat is, I'm rounding about negative 2.87. So here we want our one-sided p-value would be the probability that if I have a T9 that it's less than that negative 200 or 2.87. There are, if you look in here, no negative values. However, in fact, this is specifically looking at the upper tail. This is where we use the fact that it's completely symmetric to our benefit here. So this is equal to the probability that the same, so T9 is greater than positive 2.87. So if I have negative 2.87, this area is the same as if this is positive 2.87. And this I can find using the table. So that's what we're going to do here. So first, my degrees of freedom, they're 9. So this tells me, okay, there's I'm going to use this row. Now here's the trickiest part. I want to find where, in this case, positive 2.87 lives. So like if I look here, it's not between these two numbers. It's not between these, but you can see that the numbers are getting bigger, right? So looking here, 2.2, 2.3, 2.8. I would argue 2.87 is somewhere between these two numbers, right? So looking here, I am going to, I'm looking at my lack of space here, my one-sided p-value, so now I'm going to look up. My one-sided p-value is between these two numbers. So be really careful to note this one is smaller than the one on the left. So my one-sided p-value, 0.005, so one-sided p-value, it's between 0.005 and 0.01. However, we don't want a one-sided p-value, right? It's a two-sided test. So I'm going to multiply everything by 2. So all of these by 2. So I'm going to get 0.01. And now I have a two-sided p-value. And then 0.01 times 2 is 0.02. So my two-sided p-value, it's going to be between 0.01 and 0.02. I don't know exactly what it is, but it's between those two values there. So specifically, when I plug it into a calculator, you can find a more exact p-value. I got a p-value of 0.0184, which is between 0.01 and 0.02. So that checks out. So here, it's okay to say, okay, a p-value between 0.01 and 0.02. And if we're using the 0.05 significance level, we're going to reject. So our p-value is smaller than that significance level. So that's strong, right? We like our p-values low. So we're going to reject the null here. So rejecting the null is saying, okay, we're going to reject that average mileage is really 12,000 miles. We're going to argue that it's actually different. So here, if it's between 0.01 and 0.02, I would say it's fairly strong evidence. So there's strong evidence that, so now I have to say the alternative hypothesis is in words. So that the mean or average annual mileage for all drivers of this car, because you want to include your population in there, and then the actual alternative part, so is different than 12,000 miles. Which, if you look back to your confidence interval, it's not like a guarantee because, well, I mean, I guess it was a two-sided test. If you look at the confidence interval, so that 95% confidence interval, I'm just throwing it on here because it's where there's room. I had 7,473.208 miles to 11,462.192 miles. If you look here, the value 12,000 is not inside of it. In fact, 12,000 is somewhere above the entire interval. So since this is a two-sided test, we could know, hey, I'm going to reject the null hypothesis that it's 12,000. And I know that the p-value is going to be smaller than 0.05. I don't know how small, but if I hadn't performed the hypothesis test at all, just the confidence interval, I could have said no, at the 0.05 significance, I would reject that it's 12,000. And the p-value is less than 0.05. You just wouldn't know how much smaller without actually running the test. So that's it. Here we're going to add matched pairs coming up.